Welcome to the session, Emerging Frontiers in Earth Observation and Geoinformation Science in Antarctica. And I'm sitting with Pete here in Longyearbyen, and we have a co-convener from Cambridge, Peter Fretwell, who is sitting in Cambridge. And we have 13 talks in this session, total 4 hours of session with a break in between. And we can summarize the first lot of first time slot in the second time slot in the beginning of the second time slot. But before we start, we have some housekeeping. First important thing is that this session is being recorded. And if you would not like to record your presentation, please send an email to the organizers before 12th of August, because the organizers will put up the recordings after 15th of August. Then we have a poster session, e-posters. If you have gone through the virtual platform, it's available. All the posters are uploaded on the session. For instance, I have shared my screen here. If you go to the poster session in cross-disciplinary and put up the session title, you can see all the posters listed from this session. So we have 1, 2, 3, 4, and 5 posters. Some of you from the authors from the poster sessions are here, and if you would like to present your presentation in quick 2-3 minutes presentation, it is possible at the end of the session. So if you are interested, please stay online until the end, and then we can go through the posters one by one if you would like to do so. Then we have questions. If we have 12 minutes of presentation, each presenter will present for 12 minutes, and then we have 3 minutes for questions. There are 2 ways to ask questions. First is you can put up your question in the chat box, or if you are interested to speak, you can raise your hand, and then we can get you into the panelist list, and then you can ask the question. So there are 2 ways to do so. And with this, I think we don't have many information. I think we don't have much information on the housekeeping, but let me cross-check. Yes, so I think these are some important points to be noted before we start. And we still have 2 minutes because we will start at 3:05 for the first presentation by Professor Eileen. So if you can share your screen and be ready, and we can start in 2 minutes, Eileen, please.
It tells me that I cannot share. Oh, you finished sharing your screen. Okay. Yeah. All right. Okay. All right. Can you see that okay?
Not yet. Yes, now.
Let me see if I can do one thing here. Just a moment. Let me see if I can get my camera to come on. There we go. All right. Okay, are we good to go here?
Can you make the full screen? Yes. Yes. Okay, now we can start this. Yes.
Okay.
Thank you.
Okay. All right. Thank you. So I'm Eileen Hoffman, and I'd like to begin by thanking the conveners for the opportunity to participate in this session. I have the pleasure of being the co-chair of the Southern Ocean Observing System, along with Mike Williams from New Zealand. Elise Hancock is the SEWS Executive Officer, and Sean Henley and Seb Moreau are Vice Chairs of SEWS. The SEWS is a project that is jointly sponsored by SCAR and the Scientific Committee on Oceanic Research. The SEWS International Project Office is hosted at the University of Tasmania in Hobart. And the other sponsors of SEWS are shown on this slide, and we very much appreciate the sponsorship and support from these groups. Okay, so what is SEUS? Well, the SEUS has the mission, as you can see here, to facilitate the sustained collection and delivery of essential observations of the Southern Ocean to all stakeholders through the design, advocacy, and implementation of cost-effective observing data delivery systems. So in the next few slides, what I'm going to do is talk about how SEUS advances this mission. All right, so the first thing here I'm showing you is the Southern Ocean Science Pathway. And the red stars on this slide show where SEUS interacts with this pathway. And there are 4 primary areas. The first is through aligning priorities across the Southern Ocean community. The second is by enhancing in collaboration, observational and observing capabilities. And then also to look at ensuring the management and delivery of observations in the Southern Ocean meet the findable, accessible, interoperable, and reusable, or the FAIR data principles. And then finally, and probably the most important thing that SEUS does is it makes sure that the information gained from the Southern Ocean observations is made available to all of the stakeholders. So what does this mean? Well, what's shown here is some examples of international and circumpolar observing initiatives and national and regional initiatives, observing initiatives. And what SEUS tries to do is to integrate across these types of programs. So how does this work? Well, SEUS has just recently published a new science and implementation plan, which will guide the program through 2025. And in the process of putting together this program, there were 5 community agreed science themes. We're in the process of developing the new implementation plan. These 5 themes were identified by the Southern Ocean community as being important. And these look at it being important for observations, as you say. So these look at understanding the state and variability of the Southern Ocean cryosphere, circulation, carbon and biogeochemistry, and ecosystems and biodiversity. And fluxes provide the cross-cutting links between all these 4 major themes. Okay, so for each of these themes, the community has identified particular science challenges or key challenges. And on this slide here, I've just shown one example for each of these themes. All right, and so what SEUS will do is works to collect or to enhance the collection and delivery of data that's required to address these science themes and key challenges. All right, and in addition to identifying the themes and the key challenges for each of the theme, SEUS has also been looking at its foundational capabilities in order to facilitate and implement the science challenges and the key and the themes. So SEUS has some foundational capabilities that provide the framework to enable the development, collection, and management of these observational data. And this is shown here with in this slide, where the foundational capabilities are along the bottom here. And these are looking at observing system design, key variables and modeling, looking at making methods and standards even across the different types of data set, and also looking at the data management and delivery. And that's a very important part of what SEUS does. And also SEUS wants to make sure that all of this is done through the development of networks and coordination, and with it being done in such a way that it addresses the issues of equity, diversity, and inclusion. All right, so how does SEUS get implemented? Well, like most of the programs, there are a number of important working groups, task force, and capability groups that SEUS has. A primary one is the Data Management Subcommittee, and that subcommittee oversees all of SEUS data activities, which are the core of SEUS. All right, and then within SEUS, there are 5 regional working groups, which are listed here. And these working groups look in the different areas of the Antarctic, which is shown on the map here to the left. And the working groups identify data needs, they identify observational needs, they provide synthesis products that look at the state of the art and where we need to go next in terms of data collection, data design for observing system, or design for data observing systems, and also for identifying key science themes. The capability working groups are set up to provide SUSE with information and capabilities that are considered to be gaps in our understanding. And there are three of these right now. One is looking at censusing animal populations from space, the Southern Ocean flux or SOFLUX, and also observing system design. Then there's some task teams that are set up to do very short-term analyses, syntheses, or whatever that the SUSE community identifies as important. And then also SUSE has an equity, diversity, and inclusion group to make sure that we adhere to the principles of equity, diversion, and inclusion. And very importantly, SUSE has partnerships and collaborations with a number of groups, one of them now being the UN Ocean Decade Southern Ocean Task Team. So this is the structure of SUSE, and this is what actually gets things implemented within SUSE. But SUSE has two primary data delivery products, and they're shown here, the SUSE map and Due South, and I'll talk a little bit about these because these are one of the primary ways by which SUSE makes data available to the Southern Ocean community, or to any community for that matter. All right, so SUSE map is what's shown here. This is an example of the interface for SUSE map. But SUSE map is hosted and maintained for SUSE by EMODnet Physics from the European Marine Observation and Data Network. And what's shown on this slide is the newly launched SUSE map interface. All right, so SUSE map is an interactive map of the Southern Ocean with aggregated data layers. So you can go in and pick out what layers you want. And what's shown on this map is a temperature observations from a whole bunch of different data sources that include CTD data, animal-borne sensor data, all different types of ways in which you can get temperature measurements. And so if you actually click on the data point there, it comes up with the metadata for the data, and you can also get information about the data sets, where it is, and you can actually get to the data. All right, so this type of information is really very, very useful. And also shown on here with the blue line is the sea ice distribution, and the purple line is the polar front. So this is a very useful way to figure out what data are available and how to access the data. The other product, Due South, is shown here. And this is SUSE's database of upcoming expeditions to the Southern Ocean. And Due South is hosted and maintained for SUSE by the European Polar Board as part of its newly launched platform for polar infrastructure and logistical discovery and planning, or PolarDex, which is shown here. And what this interface allows you to do is look at past, upcoming, and planned expeditions to the Southern Ocean, cruises, land-based expeditions. Also, Due South gets direct feeds from ComNap, Camilar, IATO, and other organizations, so that you can get very up-to-date information on what's going on. And you can also, because of the information coming in from these other groups, you can also get underlying information about the vessels, the aircraft, field activities, and supporting these planned routes. And so if you've got a graduate student who's interested in going to the Southern Ocean, you could go look at Due South and see what's coming up, or even you as a scientist, and see what the possibilities might be to participate in some of these activities. So the final thing I'll talk about here is the upcoming SUSE Symposium. This is the inaugural symposium for SUSE as part of the new science implementation plan. It will be held next August 2023 in Hobart, Australia. Some of the sponsors are shown here. So I encourage you to maybe save the date and attend the SUSE Symposium. And there will be request coming out very soon for session proposals, and that will be followed by a request for abstracts later this year. And the program committee is working very hard now to design a program that will be inclusive of the Southern Ocean data delivery, data observation systems, and also the stakeholders and users of the data. So I encourage you to put this in your planning for next year. So the last thing is to say thank you for your attention here, and if you have questions, I'll try to answer them. But what is shown here is more information or websites or links about how you can get more information about the Southern Ocean Observing System and things like SUSMAP and Due South. So I'll stop at this point and thank you very much and ask if there are any questions. Thank you.
Okay, thank you, Eileen, for your presentation on SUS, and this floor is open for the questions. So from the audience, if you have questions, you can raise your hand. I can't see any question from the chat box, but if you have questions, you can raise your hand and I can allow you to speak. Okay, there is no question from the audience, but I have a quick question, Eileen. I was wondering if the data on the SUS observing system is harvested through the different data portals, or is it a distributed data system?
Yeah, it's a distributed.
Okay.
Yeah, it's a distributed data system, right?
Okay.
But what SUS does is it pulls all of that information together in one place so that you can go to SUSMAP and you can say, I want, like I was showing you, all of the temperature data for the Southern Ocean. And you can make the data layers and pull in the information from all the different data sets. All right, so it's a really nice product. It's a nice way to visualize the data, visualize the data distribution, and get information, on how much was there, when it was taken, and then you can then download the data sets and use them as you want. All right, as an example, I use this in one of the courses I teach. I give homework problems to the students that require them to go into, something like SUSMAP and look at the data sets. So it's good for that education as well as a researcher looking for all of the data that are available on a particular type, particular type of data.
Okay. Thank you, Eileen. And now I will check it again if anyone from the audience have questions. Seems not. Okay, but thank you very much again, Eileen. And then we will move to the next speaker. The next speaker on the list is Matthew Ellis, who will speak on potential of satellite-derived bathymetry mapping in Antarctica using high-resolution multispectral imagery. So Matthew, can you please share your screen?
Yep, thank you very much, Jawak. Let me just give me a second here. How's that looking?
Yes, fantastic.
Awesome. Well, hello, everyone. My name is Matthew Ellis, and I am the manager of satellite derived bathymetry at the Australian Hydrographic Office. And I'm very excited to be with you all today to present some of the findings of a pilot project I participated in, investigating the potential of satellite-derived bathymetry mapping in Antarctica using high-resolution multispectral imagery. So there was a couple of motivations behind, starting up this project. Basically, back in 2017, no known attempts at producing satellite-derived bathymetry in Antarctica had been undertaken, and I believe that's still true to date, although please feel free to correct me. And as we all know, bathymetry is a fundamental data source for many scientific, hydrographic, environmental, activities in the Antarctic space. So we wanted to sort of answer the question, can we use satellite-derived bathymetry to fill in these critical data gaps over the shallow water areas of Antarctica. To give you a bit of a background on satellite drive bathymetry, or SDB for short, SDB is the mapping of water column depth using a spaceborne sensor. There's quite a few different ways that people can do this. For example, the Canadian Hydrographic Office, I think, has done a lot of research investigating WorldView 2 photogrammetric approaches to deriving bathymetry, but the most common by far is using multispectral imagery and deriving depth using, reflectance values. Most SDB models can be categorized into one of two categories. The first of which we're going to talk about today, which are empirical models, where we basically are taking known depth values and regressing or modeling them against some sort of remote sensing reflectance value. And the second of which is physical inversion models, which are basically a bit more advanced analytical type models that solve the light physical equations. The benefits of satellite drive bathymetry are it's cheap, it's quick, and importantly for Antarctic context, you can use it to access areas that would normally be denied or are too remote to map using a vessel-based echo sounder, and also has very high horizontal accuracy. But some of the limitations of satellite drive bathymetry are that the vertical accuracy is not quite as accurate or precise compared to traditional echo sounder-based hydrographic surveying techniques. And it also struggles quite significantly to map depth over dark and thick substrates, which we can probably all appreciate quite common around Antarctica. So we had three main objectives for this pilot program that we wanted to sort of figure out. The first of which was, is this even possible? Basically, the conditions for aquatic remote sensing in Antarctica are very challenging, so we weren't even sure whether we'd be able to derive any meaningful depths. The second was, what type of empirical satellite drive bathymetry algorithms work best? And the third thing we wanted to achieve is to sort of identify what challenges there would be to upscaling this to a more regional scale approach. Our study areas for this pilot program were Davis and Mawson Station around Antarctica. You can sort of see from the two graphics we have up there that we had access to quite large WorldView 2 images, but our hydrographic training data was really limited to what was around the bases. And this is sort of something that I imagine is quite prevalent around Antarctica, that pretty much all of the hydrographic data we have access to is really limited to around the bases. And, that really limits the sort of empirical approaches that we can undertake in terms of satellite drive bathymetry for the rest of the continent. If anyone's interested in any of the metadata for our input data sources for this pilot program, we had WorldView 2 imagery, which was supplied by the Australian Antarctic program, and we also had some high quality multi-beam echo sounder data sets that were provided by the Australian Hydrographic Office. Our methodology workflow is up on the screen now, which you're more than welcome to have a look at. This is a pretty simple and standard SDB workflow. We weren't trying to reinvent the wheel with this pilot program. We were much more interested in seeing, is this possible and to what extent it's possible? Some of the things I thought might be interesting for other attendees in the audience today, if they were ever going to attempt doing some similar work, is that we initially wanted to implement some of the cool land and snow masking indexes that were identified by Jawak. Hey Jawak, how you going? But unfortunately, in one of our images, we had a severe banding in the red and near infrared 1 bands, which didn't allow us to use these indexes. So instead, we used the pan band, which actually ended up being pretty good at masking out land and snow areas. The benefit of which was we were able to do sub-pixel iceberg detection and mask those areas out, which was quite cool. And probably the biggest challenge we had in our pre-processing workflow was optical deep water masking. Even in tropical areas where satellite drive bathymetry is much easier to accomplish, this can be quite challenging. And we attempted a simple thresholding of yellow and green bands and found that even though it would work quite well for the specific area that we derive those values from, you really need to attempt some sort of spatially weighted approach when dealing with some of these larger WorldView 2 images. We investigated 3 different types of satellite drive bathymetry models. The first of which is a blue-green band ratio model. This is really the simplest form of satellite drive bathymetry you could think of. it was first derived by Stump back in 2003, so it's quite old, and it's really just taking the log ratio of 2 of our bands from our satellite image and regressing that against some known bathymetry values. The second model we looked at is actually the same as the first, but instead of just using the green-blue band model blindly, we actually regress every unique band combination available in the imagery. So for WorldView 2, that means there are 28 bands. And we look at the correlation between every single one of these band combinations in our training bathymetry and identify which of the band combinations is actually best suited for bathymetric mapping. And the third model is a really cool model that was produced by Nurman and Jadidi, and his research group out in Italy, which is called the sample-specific multiple band ratio technique. This is a really cool sort of empirical model, and if you're interested in this, I'd highly recommend checking out the paper listed there. But basically what we need to know for this presentation is that instead of just using a single band ratio, what we're doing is we're taking multiple band ratios from the image and identifying which, for our prediction pixel, we're identifying which of these band ratio models work best for spectrally similar pixels in our training data set, and using those based on a KNN inverse distance weighting algorithm. So our results for our OBRA, or optimal band ratio analysis, are up on the screen now. And what's really interesting about these results is that you can sort of see that the highest correlation was found almost exclusively with bands that had the yellow band combinations that had the yellow band as one as the band participants. This was quite unusual from my experience, at least processing satellite drive bathymetry from WorldView 2 images outside of the Antarctic environment. And I think it has some pretty significant implications in terms of, sensor development, or, you're going to try and put a multi-spectral sensor on a UAV. So yeah, we basically found that unlike, if you're mapping a coral reef or a temperate beach somewhere where, the green-blue band ratio would be expected to perform best, down in Antarctica, we found a lot of, correlation occurred with that yellow band space. Our results for Davis Station are up on the screen now, and you can sort of see that the green-blue band ratio model unexpectedly didn't work very well. However, once we identified that the yellow and coastal band ratio model was a much better performer, we used that as our band ratio, and achieved a lot of improvement to our correlation and our error values. And this was, that's what we sort of noticed again when we implemented the smart SDB model. These, results may not be the best, but considering the very unique and challenging environment in Antarctica, we were actually pretty happy with this. And I think this sort of shows that what we are trying to achieve here is that we're trying to answer the question, is this possible? And looks like the answer is yes, to an extent. Similarly, for a Mawson station, we had that same sort of story happening where the green-blue ratio model doesn't perform too crash hot, but once we've identified the yellow band models work a lot better, we do get some increases to our accuracy. However, the smart SDB model is the clear winner here. And I think this goes to saying a lot that these multi-band approach is the way to go when we're talking satellite drive bathymetry down in Antarctica. One thing I would sort of caution against here is thinking back to our study area, these multi-beam surveys are really concentrated in one specific location around the bases. So I would not expect this accuracy to be replicated around our entire SDB data set, but that's just a limitation of the in-situ data we have access to. So our key findings were basically, we wanted to answer the question, is it possible to produce satellite drive bathymetry in Antarctica? And the answer is yes, which is exciting. We mapped down to 5 meters in Davis and 7 meters at Mawson using our WorldView 2 images, and found that the yellow band performed extremely well. In terms of what type of algorithm works best, it was pretty clear that a multi-ratio approach produced significantly more accurate measurements compared to a single ratio approach. And this is something that if I was going to replicate these studies, I would definitely be looking at smart SDB or a similar empirical algorithm that really utilized the benefits of having multiple bands. The third objective we wanted to look at was the challenges to upscaling this. Basically, what is going to prevent us from developing a regional sort of workflow to map not just the areas around the bases, but in the more remote parts of Antarctica. The biggest challenge is basically the availability of in situ bathymetric data. As I mentioned earlier, most traditional hydrographic data is localized around the bases. However, since this project was conceived, the ISAT-2 satellite run by NASA was accidentally discovered to be able to detect the seafloor using its Atlas sensor. And now that it's been running for a few years now, I'd be hopeful that there's been a couple of summers where the sea ice has been in the right conditions for seafloor detections in its 3-month temporal pass. So that could be something that we look to in the future as more of that data becomes available as a training data source and solves our problem of most of our hydrographic data being located at the bases. And the other big challenge to upscaling was that, due to the time limitations we had in this pilot program, we couldn't build a lot of custom tools to do a lot of thresholding and masking. And if I could, go back and redo this, what I would definitely be looking to implement is some sort of regional or spatially weighted implementation of some of these pre-processing steps. One thing I'd like to comment on is about imagery sources. So we use WellView 2 imagery for this, which obviously has a yellow band and has, let's say 6, if we're not going to include the near infrared bands that could be used potentially to map water depth, if we're going to say that the red edge band could maybe map to the first couple of centimeters of the water column. So I'm unsure if these results would be able to be translated to Sentinel-2 or some of the newer satellites we see these days, which don't have quite as many bands. They're focusing more on high spatial resolution. They only have 4 bands. So something to consider if you're ever involved with a project that you're trying to put a multi-spectral sensor on a UAV or something to do bathymetry in the future, is maybe a yellow band is something you need to consider advocating for. Thank you very much for listening to this presentation. I hope you found it interesting or useful. I'd just like to thank Geoscience Australia, the Australian Antarctic Program, and the Australian Hydrographic Office for their support of this pilot program. And in particular, I'd like to shout out to colleagues at Geoscience Australia, Jody and Steve, for all of their help and guidance on this. And if you have any questions, happy to answer them now, or my email is up there if you would like to contact me outside of the event. But thank you very much, everyone. And thank you to the Convenors for organizing everything today.
Thank you, Matthew, for your presentation. And I can see from the audience if there are any questions. You can raise your hand. Okay, I don't see any raised hand. Thank you, Matthew, again for your presentation. I have a quick question for you. You have used the STUMP model for deriving this bathymetry, but did you also try the Lysenga model, which uses multiple bands than the 2 bands?
No, we didn't go back and use the Lysenga model. We were sort of thinking in the scope of this, we weren't actually trying to test every available model we had access to. It was more of a, is this possible at all? And looking at more what is able to be implemented in the 2 months we worked on this last year. So we didn't have a look. I expect that there wouldn't be any significant differences to what we sort of showed here, that, I would expect the Lysenga model to have performed pretty similarly to the STUMP. It's really that sort of multi-band approach, which has only become quite popular in the last 5 or so years, that I think allowed this to be quite a success.
Okay, thank you. And there is a question from Peter Fretwell. What was the deepest depth you could measure with the confidence?
Thanks for the question, Peter. So it was 5 meters at Davis and 7 meters at Mawson. Basically, what we did sort of witness when we were interrogating the imagery is that after those first few meters of water column depth, even though we could still see the seafloor, there was no meaningful signal differentiating the seafloor from a deep water area. So I think that's one of the big challenges for satellite drive bathymetry in Antarctica, is that acquiring suitable imagery where we can sort of get down to deeper depths. At the moment, it appears that WellView 2, we're sort of limited to that 5 meter mark.
Thank you, Matthew. And there is There is one more question from the audience, says how generalizable is your model to other areas, assuming data are available?
Sorry, Joe, could you repeat that question? I think I just missed it.
The question is that, can you transfer this model to other areas if the data is available?
Yes, no, 100%. If you were able to get in situ bathymetric data, this is 100% implementable around Antarctica. Basically, the biggest limitation is having some bathymetry. If you have bathymetry, this is not that difficult to implement at all. And I believe that there will be a report published with the data sets that we produce in the coming months on the Australian Antarctic Data Centre, which would be very helpful in implementing this for your own uses.
Yes, thank you very much, Matthew, again. And I think we are on time, and it's time for our next presenter. And the list is Dr. Alvarino Luis, who will speak on spatiotemporal change analysis for snowmelt over the Antarctic shelves using scatterometers during 2000 to 2018. Dr. Luis, please.
Yeah, good evening, everyone. Am I audible?
Yes, can you also share your screen, please?
Yeah. Just a minute. Is it visible?
Yes.
Okay. Good evening, everyone. This is Alvarino J. Luis from Goa, India, and I'm going to present spatiotemporal change analysis for snow melt over the Antarctic ice shelves using scatterometers, and we have taken the period from 2000 to 2018. And I'm happy to introduce my co-authors, Mr. Alam Mahfouz and Shridhar Jawak. Yes, he was with NCPO at that time when this work was carried on. Okay, now a brief introduction about the need for this type of analysis. Basically, the global climate change, when we look from the cryospheres, it is due to the sea level rise caused by ocean warming, at the same time addition of fresh water, that meltwater that runoffs from the cryospheric regions, both poles, and the surface and the basal melting on Antarctic region can be seen as a major contributor for a sea level rise. And this is one of the point that has been raised by IPCC report, recent report. And the ice shelves are very sensitive to direct interaction with the atmosphere as well as oceans in the form of temperature change. Both we have ocean warmer temperature coming from the circumpolar deep water. At the same time, atmosphere also has warmed, and a couple of papers are pointing to that particular phenomena of the Antarctic Peninsula being affected by the warm air temperature anomalies. And the ice shelves buttresses the ice sheet. So the loss of ice shell could accelerate the flow of non-floating ice near the coast that can lead to retreat of glaciers. And to have all these things monitored and to do a study, we need a very good data set that can cover both spatially and temporally. And this remote sensing data serves as a good tool to study the ice sheets and as well as the ice caps. Now, this is the study area. So for convenience, I have divided the study area into 4 parts. We have the Antarctic Peninsula region, including the riser ice shelf. Then you have the northern ice shelves, just shown here, which is Ronnie Fisher. Then we have the eastern ice shelves comprising of the Emery ice shelf and Shackleton. And then we have Getz as well as the Ross ice shelf. So this is, I will be mostly focusing on the areas that are shown here, so that we have a mean picture of what is happening in those ice shelves, and we can compare the different ice shelves. Now, this is the data we have used. Scatterometer data comes from NASA, that's QuickScat. Then we have OceanSat-2 launched by ISRO. Then METOP A data that is by European remote sensing, and we have scat.
Lewis, I don't think your PowerPoint is moving on. It's still stuck on slide 2.
Sorry.
I don't think your PowerPoint, your presentation isn't going forward. It's still on slide 2. I don't know if that's right.
No, I'm not. It's not shared. The screen is not shared.
No, the screen is shared. Your PowerPoint presentation doesn't go further. Is it on the second screen, second number of slide?
Yeah, this is the third slide.
Okay. Yeah.
Can you see now the fourth slide?
No.
No, it's not moving. We are still in the introduction. Yes, now we can see data.
Okay. Okay, so this is this thing now. The incident angle is different for different platforms. So what we have done is we have normalized using the SEER function, and this is the normalization value for B. We have a combination of two constant A and B, and this is the angle, incident angle. So we have taken care of the the back scatter normalized from the SEER products. So having seen the main data, we have also used auxiliary other data sets like automatic weather station, particularly Davis station, air temperature, which is nearest to the Emery ice shelf. And this data set extends from September 2001 to 2018. We have the reanalysis data. This is we have used so that we can understand how the temperature advection takes place in those regions and which are the shelves that experience the maximum temperature advection. So we have used from ERA4 data, and these parameters from this ERA4 include net solar radiation, net long wave radiation, latent heat flux. So this first four accounts for the net heat fluxes, and we have also used the pressure charts and the 2-meter temperature as well as the wind. And this is 12 hours temporal resolution and 12.5 kilometer spatial resolution. So this is the method we have adopted for the melt detection. We have used a very commonly adopted melt pixel detection algorithm, which is a melt pixel is detected if the normalized backscatter is less than the winter mean minus 3 times the winter standard deviation minus a constant C. Now this is now the trick is on a constant as well as the winter standard deviation. Now basically what we have done is winter standard deviation we have taken, but the idea here is that our C value is different from others which have used different values. So we have used C of 1 dB compared to other people because we have done some couple of experiments to detect with different type values of C. So and we found that C is equal to 1 is the optimal way of tracking the melt over the ice shelves in Antarctica. So now this is the melt onset date is quite tricky to determine, and because we can get a lot of what we call false alarms using that algorithm. So what we have done is we have considered 5 consecutive days to be under melt. Then we take that first day as the day of the melt onset, and then we add up all those 5 consecutive days and to make the total duration of the melt. So we have the melt onset date determined, then we have the duration of the melt. And here is a typical example when we have compared with the Emery G3 AWS site, where we have a typical inverse relationship between the backscatter and the air temperature from that particular AWS. So having seen this, we'll go right into the results, and the mean melt days for this particular areas of the shelves. We have taken A, B, C, D. Here top is the melt duration. Now what we have see is at mostly focusing on the Larsen Sea as well as Riser ice shelf. What we observe is First thing is the variability is the melt duration extends. The highest is about 75, and it goes down to about 20. And what we observe is a sort of a decreasing trend in this thing, but there is not significant statistically. But for the B region, we have found is there is not much of what we call trend. But what we observe is that melt is lower compared to A region. For C, we again have a decreasing trend. That is, we have now on the east coast, which is Emery Ice Shelf and Shackleton and west. So here we have a significant decreasing trend. As for the area D, we have also a decreasing trend, but the compared to area C, we have relatively higher melt duration over the period of 18 years. As far as the melt onset is concerned, we are at region A, we have very early ice melt that is taking place in the mid-December, and it goes down to, even it happens in as early as 26 October during the recent year. As far as B is concerned, we have the ice melt a little later, that is between the 5th and 25th December, and 2009 we have observed that it has been delayed to 14 January. This is a very striking difference that we observed with very late melt detection. And for ice, for the ice shelf on region C, we have relatively less variability. It is between December, first week of December to about 16th December or so. And D is similar, likewise, it shows like it has little shifted onto the end of December, but not much of a trend is observed for C and D. So this is the spatial variability of melted duration. So I have summarized, it is too cumbersome to go to each of these maps. So Antarctic Peninsula, we have Larsen C, George, 6 and Wilkes experienced maximum melt days on average with about 70. The melt onset was 25th November, and the mean melt duration was about 60 days. Okay, for those 2004, 5, 5, 6, and 6, 7 continuously for this particular, we got relatively, I mean, the 60-day melt duration was recorded. And this happened in the first to second week of November for Antarctic Peninsula. It is relatively earlier. Now, compared to Antarctic Peninsula, let's move on to the eastern ice shelf down. That is a region we have experienced less amount of melt duration, about 40 to 50 days compared to this mean about 60 for the Antarctic Peninsula. And this is the melt onset date was little later, that is mid, almost 1.5 months later. And the Ross ice shelf did experience melt only for a certain period of time. As you can see, we did not detect much melt, but did happen on the what you call the eastern, on the western side. And that melt was about restricted to about 10 to 20 days, and it happened the first week of January. Okay, so now this is the comparison of different shelves. I have taken only 5 shelves which are taken on different parts of Antarctica. So this is showing the relationship between surface air temperature and correlation. So it's a nice correlation is being found in the melt area. Okay, and this is 0.7 and significant at 99%. Whereas for GATS, we did not get any significant correlation. As far as Shackleton is concerned, we are moving towards the east. We got a good correlation, which is significant at 95%. As far as Emery, yes, 46.46 or 46%, which is a significant 95. And Fimble ice shelf, very high correlation, which is 99% between air temperature and melt area. And these are the some of the particular examples during 1718. We have a strong melting signatures found in Larsen C. Then we also have Fimble ice shelf. As you can see, the days about it extends to about 18 to 30 days. So this is a scenario that we have, and what is could relate to the air temperature, that is the atmospheric forcing. Now this is showing the ice shelves, the met onset date. Now Emery ice shelf, which is on the eastern hill, it experienced later compared to all other. It experienced between January, mostly in January. But Larsen ice shelf had the earliest onset date, where maximum melt also occurred on 1st January. Whereas the latest is the Fimbul and Getz, shows around 12th January. And melt versus, we also tried to relate whether there is any remote forcing involved in this melt scenario. So we found a correlation for area C, which is this region that is on Emery ice shelf. So we have a strong correlation about 0.57, which is which is significant at 95%. As the same time for D area, that is north, we found 52. So, but other ice shelves did not show, for at least for Southern Oscillation Index, we did not get a good correlation, which is statistically significant. But SAM did show a good correlation. So to some extent, this ice shelves, just as the sea ice is also influenced by this remote forcing. So there is also a relationship between remote teleconnection between the SAM and melt area and melt duration. Now, this is one of the mechanisms how the surface melting of the ice shelves takes place. So we have used here the ERA data, and we have shown the temperature advection. For example, during the mean scenario for Emery ice shelf shows that there is an advection from the ocean side into the interior. And we have a very good matching between the warm advection, and we have a strong melt in this region, which is about 20 days. Likewise, for Larsen Sea, we also have advection coming from the seaward side, anomaly, warm anomalies, they affecting this melt. And one example how the Larsen ice shelf, this A68 carved during 2017. Now 2016, there was strong melting signatures found here, and this lasted for about 30 days to 40 days. And this was constantly observed during both the years. So this may be one of the reasons why this ice shelf, why the iceberg could have disintegrated from this ice shelves. And this was observed many years as well. So comparison, what we have done is we have compared our work with Botale et al. 2015, and we see that there is almost a 1 month shift in our melt detection, maximum melt, what we have detected, and Botale et al. Have detected for the shelves that we also have selected. Now we are working on this to find out what could be the reason why there is a shift of 1 month, including those period that both the data sets were same and coinciding. So the carry home message is the melt duration has been recorded maximum over Larsen Sea ice shelf, which is more than 80 days at some location, and the minimum of less than 5 days were detected over Fimbul ice shelf. The pattern of melt extent starts in the first week of November with maximum at the end of December or first week of January, and there is a decreasing melt in the first to second week of February. Air temperature and melt area are highly correlated. At some melt shelves, net heat flux was found to be a major contributor to advection of the heat from the ocean side, while other shelves experience advection of warm air anomalies. Now the calving that has taken place on the Larsen Sea ice shelf during July 2017 has been initiated by large extent of melt and high duration during 16 over the eastern coast of Larsen Sea. And this is all I have to offer you. Thank you so much for listening patiently. I'm done. Any questions? Yeah.
Thank you. And I think we don't have enough time for the questions because we are running behind the schedule. But if you have any questions, please put your questions in the chat box, and then Dr. Lewis can respond on that. So thank you very much. And next presentation, and that's Mary Athard, who would speak on finding a needle in the haystack, monitoring albatrosses from space using satellites and citizen science.
Hi, so I think I have pre-recorded this, so I don't know if the IT team at SCAR is able to present it because it's boiling hot in here. So we probably have the fan on between the three of us in the room currently.
Yeah. IT team,
otherwise, I can share my screen and do it that way.
I will ask IT team if they can do it.
Can you hear me?
Yes.
Yes, I have a pre-recorded talk. Is the SCAR IT?
Yeah, we are sharing the screen.
Thank
Yeah.
you. My name is Marie Attard and I'm a postdoctoral researcher at the British Antarctic Survey. Today I'll be talking to you about our project to monitor albatrosses from space using satellites and citizen science. The wandering albatross is the largest of the great albatrosses and are classified as globally vulnerable by the IUCN. Unfortunately, their populations have been in decline in most long-term monitoring breeding localities, including Gough Island, Macquarie Island, Crozet Islands, and South Georgia. Counts of albatrosses are important to monitor population sizes and trends for conservation purposes and their knock-on effects across food webs. To date, albatross surveys have mostly been based on counts of nests from the ground or yacht-based photography during incubation. However, monitoring the world's threatened albatross species using these traditional methods is challenging because of their remote nesting locations, making such surveys expensive, infrequent, and often incomplete. In contrast, advancements in satellite technology may provide a solution by improving the frequency of albatross surveys at a fraction of the cost and time required. Wandering albatrosses are ideal candidates for surveying by remote sensing as they are large-bodied, they nest in open, grassy landscapes, and they also have high contrast with their surrounding environment due to their white plumage. Previous research by our group has shown that wandering and northern royal albatrosses can be seen from space using 31 centimeter resolution satellite imagery. The satellite image on the left-hand side here, called a tile, is an example of what we would normally give to a volunteer. This one contains several different albatrosses. Can you see them? Let me give you a few hints to help you find them. First of all, each white to cream coloured dot is a single albatross. So when you look at the zoomed in image on the right hand side here, you'll notice 4 white pixels in the middle. So that's a single albatross. Secondly, when you look at the tile itself, when it's at 150 by 150 meters, they'll actually look like a breadcrumb. And so it's recommended that you zoom in order to search for them. And lastly, the nests are usually between 5 to 50 meters apart. There may also be other albatrosses in closer vicinity to other individuals if they're a breeding pair there at the same time, or if there are non-breeding birds wandering around the island. The reason we use 150 by 150 meter tiles is because you can see other landscape features, which makes it easier to see the albatrosses based on the relative size differences between these different landscape features and that of an individual bird. And so here you can see the 5 different points which are separate individual albatrosses. For this year's Citizen Science campaign, we focused on albatrosses in South Georgia only, which is a collection of remote and inhospitable islands in the South Atlantic Ocean. South Georgia supports the 3rd largest breeding population of wandering albatrosses. Regular and effective monitoring using traditional ground-based survey methods are currently limited to only 3 accessible islands, and very little is known about the many remote locations found elsewhere, which are pointed out here with the arrows many of these are pretty much unpopulated and very, very, very difficult to access. In terms of the crowdsourcing campaign, we were able to incorporate 47 different satellite images across these 20 different breeding sites. We also were able to incorporate multiple images for some of these sites, ranging from images taken from 2015 up to now. All the images were taken between January and March, which is the peak time where the eggs are being laid. So this is the best time to do it because there should be a lot of breeding pairs available at that point in time. The area covered in the campaign is based on the maximum possible extent of albatross nest sites, called nest site boundaries. To determine this, we used a combination of nest GPS coordinates from the last island-wide census, in addition to slope and vegetation data that we were able to map on top of each locality. So in this example, the little yellow dots are each individual albatross from a previous survey, and that purple region includes areas where the habitat was found to be suitable potential nest sites for albatrosses as well. And so any region in the middle here was highly mountainous, very sloped, and didn't have any grasslands, and so was considered to be not part of the nest site boundary. In total, the campaign covered an area of 150 kilometers squared, divided into 6,589 tiles. We are asking volunteers to spend at least 30 minutes searching through these tiles, and we anticipate that each volunteer on average will count between 50 to 100 tiles. Multiple observers per tile are required to analyze and accurately assess the reliability of these counts. As such, each tile will be counted by at least 6 different observers. Our aim is to attract over 1,000 participants. This task is ideal for adults, high school students, as well as university students. In order to reach this many people, RSPB have kindly offered to advertise and promote our campaign to all their RSPB members through their e-newsletter. The only thing that's required by volunteers is access to a laptop or iPad, and it's recommended that they don't use their mobile phones because the screen will be too small to detect any albatross individuals. Volunteers are asked to create an account on the GeoHive platform run by Maxar, and then complete a tutorial on how to be an albatross detective. They can then start searching through the satellite imagery straight away. Their task will be to tag each albatross they can find in each tile. So this is what the albatross campaign actually looks like. And so it has the tile on the left-hand side, which has zoom features. It also has image adjustment controls to change the brightness, sharpness, and contrast. It then also has these 3 buttons, which you can see in the middle. So if you see an albatross, people are asked to press the albatross button, and then a marker will appear as their cursor, which allows them to tag the exact location of where these individuals are found. If they don't see any albatross, they're asked to select no albatross present, and then they're taken to the next tile. And if the image is really poor, for example, if it's filled with cloud cover and we can't actually see past that point, they're asked to press the poor image button, and once again they will be taken to the next tile. The other feature that we have as part of this basic campaign is a static information page, which is shown on the right hand side, that they can open up at any point in time. It goes through all the instructions needed in order to find albatross, examples of tiles with and without albatross, as well as further information on how they can help save albatrosses outside of this campaign. So you may be wondering, where is this campaign? Is it live? And how do I sign in and get started? And so unfortunately, it hasn't been released yet. We've had a few delays. Originally, it was intended to be made live on the 19th of June to coincide with World Albatross Day, but due to issues in terms of trying to get the contract signed for the campaign, and also issues in terms of the prototype that needed a bit more refining and touch-ups, meant that we decided to delay it to the 29th of July, but we still had a few more issues with the campaign in terms of the layout, and so that's once again been delayed for at least another 2 weeks or so. So we're hoping that it should hopefully, fingers crossed, be released sometime this month, hopefully within the next 2 weeks or so. And as I mentioned before, the campaign will be running continuously until all of the tiles are counted by at least 6 observers. We think that it would probably take 2 to 3 months to run. We might decide to continue running it even longer if we see that there's a lot of interest from the public and from schools and universities that want to use this as an educational resource, but we'll see how we go. In addition to this, we've recently submitted a Darwin Plus grant, which basically will be attempting to get funding to use the crowdsourced data as a training data set for automated detection of wandering albatrosses. Various members of our team have been working on different methods of automated detection of albatrosses and have seen quite a lot of success in that area. And so we just need a bit more data to really refine that methodology. And so this is one part of what we're hoping this huge, amazing data set will allow us to achieve. To find out more about the campaign and when it will go live, feel free to follow us at Albatross Space on Twitter. I will be putting up when it goes live and the link, so then you can register and start counting some albatrosses yourselves if you want to be a detective. It'll also be posted on our Bass Albatrosses from Space website as well, which I've included the link below. One of the limiting factors at present is the number of the high resolution satellites available. Until 2021, there was only one 30-centimeter satellite in orbit, which is Maxar Worldview 3 shown here. So this is the one we're using for all of our satellite images for this campaign. However, Airbus launched the first of full 30-centimeter satellites in late 2021, and Maxar will be following this this year with the launch of 6 further 30-centimeter satellites. This escalation of capacity should greatly increase the chance of successfully tasking imagery that is time dependent, such as with the albatrosses that only breed during a certain period, and also in areas that have a high percentage of cloud cover. So looking into the future, we're really hoping to take advantage of these new advancements and having all of these new satellites in orbit, so we can take more imagery of albatrosses at different times during their breeding season, for example, so we can distinguish between breeding birds and non-breeding birds. And so hopefully we'll be able to create a long-term data set that's assessing variation and changes over time in albatross populations in South Georgia, and then hopefully extend that to an ocean-wide census as well, which has never been done before for this species. I would like to thank all the key investigators, collaborators, and field teams that have made this project possible, particularly various people that have collected GPS data and habitat data in order for us to complete the project. The funding was provided by the South Georgia government and the Darwin Plus initiative as well, which we're extremely grateful for. Thanks very much for your time.
Thank you, Mary, for your presentation recording. And the floor is open for questions from the audience. I don't see any raised hand from the audience, and I don't see any questions from the chat box. But IT team, can you unshare the screen from the video?
think that's IT.
Oh, wait, I can do that maybe. Yes, I can do
Here
it.
we go.
Yes. Okay, thank you very much, Mary, again. And hopefully this crowdsourcing activity goes well now, and then you get more of the data, long-term data, and we hopefully see results by next year, maybe.
Yeah, hopefully.
Yeah. Yes, and thank you very much for attending the first time slot now. So it's a time for a quick break, and we have around 15 minutes, and we will be back after around 15 minutes, and then we move to the next time slot. But those who deliver the talk now, maybe if you are interested, we can capture a group picture for the social media. Yes, if you can turn on your camera, those speakers. Yes, and let me check. How can I do this? Let me check with my computer. How can I take the screen of this? Yes. Oh. After 3 seconds. Okay. I think I didn't capture this one. I need to do it again. Print screen. And thank you. And see you after 15 minutes. Thank you very much, and stretch your legs, have coffee. Okay, welcome back to the next time slot of this session. So we had around 7 presentations before, and then now we move to the next time slot. Those who have joined now, there are some information points for you, those who join now. So the entire session is being recorded, and it will be made available on this SCAR YouTube channel after 15th of August. If you don't like to be added on this recording, please contact the organizers. And there are 2 ways to ask questions. You can put up your question on the question and answer box or the chat box, and then if you would like to ask your question live, you can raise your hand, and I can allow you to speak. So. Okay, so summarizing the first session, so we covered talks which are mostly focusing on the monitoring the walruses and albatrosses using the high resolution data sets. Also, the first talk which focused on the SOOS, the Southern Ocean Observing System, and how it works. And then we had a couple of talks on ice shelves, like one from Dr. Lewis on snowmelt over the Antarctic ice shelves, and the second one was on the Gates ice shelf, morphodynamical changes in the Gates ice shelf. And then finally, we finished the session with the albatrosses from the space. So with this brief summary, we now move to the next time slot of this session. And let me invite the first speaker, Emma Mackey. Can you please share your screen?
Sure. How's that look?
Yes, perfect.
Great. Well, thank you for having me. My name is Mickey Mackay. I'm an assistant professor at the University of Florida, where I'm the PI of the Gator Glaciology Lab. And I'm going to talk about our group's ongoing work to create open source geostatistical simulation tools specifically designed for modeling ice sheet conditions. So as we all know, the subglacial conditions are critical for modeling ice sheet change. And a lot of the methods I'm going to be talking about today can be used to characterize all sorts of ice sheet conditions, from internal layers, the geology to marine sediment, but I'm going to be focused mostly on the topography and the bed roughness. We have extensive bed measurements across the Antarctic and Greenland ice sheets. However, these are not exhaustive, so these gaps have to be interpolated, for example, with Peter Fretwell's work. So most approaches to interpolating these flight lines are deterministic, meaning that they optimize local accuracy, but don't reproduce the texture or statistics of the topography. So on the left is some ice-free topography in Greenland, where I pulled out some lines from the data to represent a radar survey. And I did a Kriging interpolation, which is a traditionally used geostatistical interpolation method. So this is what the bed, could really look like, and this is the kind of information we use in ice sheet models, and it's a lot smoother. Alternatively, we can use geostatistical simulation, where the objective is to reproduce the statistics of observations. So if you have some bed elevation measurements represented by these blue dots, what we do most of the time is we're finding the best fit line that's designed to come up with the most accurate bed elevation value at a given location. But with geostatistical simulation, we stochastically simulate multiple different realizations that reproduce the heterogeneity of observations and sample the uncertainty space. So instead of one solution, you can create hundreds. And this produces something that looks more geologically realistic. So this is useful for ice sheet modeling. We have a paper in review led by Rob Law at Cambridge, where we've compared, where we've applied an Elmer ice sheet model to both bed machine and some of our simulated topography. And we found that the simulated topography produces much more heat and internal deformation at the bed. And this is actually in agreement with borehole measurements in this region at Jakobshavn Glacier, which show this very thick temperate layer near the bed. So we think that with this realistic looking topography, we can better capture the actual sliding characteristics and deformation behavior of ice sheets, and potentially produce some insights into sliding laws. Simulated topography can also be used in a Bayesian sense, where you could run many analyses using the different realizations of simulated topography. So for example, we can generate hundreds of realizations of the topography and apply subglacial water routing models to each of these, and use that ensemble of models to get an estimate of the locations of subglacial flow paths and their uncertainties. And there was also this study that came out recently, which was modeling retreat scenarios for Pine Island Glacier using bed machine and simulated topography. And they found that with their simulations, there was an added 25% uncertainty to retreat. So topography can be used in this uncertainty quantification objective. Okay, so hopefully I've convinced you that geostatistical simulation can be really powerful for improving uncertainty analyses in ice sheet modeling and better characterizing basal conditions. However, geostatistics has been historically used for mineral and oil exploration, where, for example, where you might have borehole measurements that you're trying to interpolate of permeability or porosity. This is an example where someone was simulating, I think, sand and silt facies in the earth, because the heterogeneity of the lithology is important for fluid flow. So most geostatistics tools are designed with these sorts of applications in mind. And the problem is that ice sheets are a little different. We have extremely large remote sensing data sets, where we have, instead of point measurements, we often have line measurements. The data sets are really big. There's a lot of variability in the topography or spatial statistics across an area. And we also have all kinds of measurement error and noise and things like that. So right now, existing geostatistics tools are not really ideal for doing the things that we want to do in glaciology. Also, because most geostatistics software has been designed for oil and mineral exploration applications, they can be quite expensive. Sometimes licenses can cost upwards of $10,000 per year. And they can crash when you load in large data sets, and they don't have the algorithms that can account for the complexity or variability of geologic phenomenon in ice sheets. So what we need are more robust open source tools that can work on a variety of operating systems. And we also need GPU, graphics processing unit options, so that we can run large scale simulations. So to that end, my lab has been working on developing the Glacier Stats software package, which includes geostatistical algorithms specifically designed for ice sheets. We're building on the open source GeoStats Py and scikit gstat Python packages where we can. And we have an early version already available on GitHub. So one of the main algorithms that we're using for this package is sequential Gaussian simulation. So this is a simulation algorithm that treats geologic phenomena such as topography as a Gaussian process. So if we have some unknown truth topography in gray with some measurements in black, these black dots, when we want to simulate a grid cell, what we do is we randomly select a location to simulate. We use the covariance information or the spatial statistics between measurements and their distance to this unknown location to estimate some probability distribution of where we think the bed is. And if you were doing a Kriging interpolation, you would select the mean here. But because we're doing simulation, we randomly sample from this distribution. And then that simulated value becomes treated as the conditioning data, and we repeat this process over and over until every grid cell is populated. So this is why it's called a sequential algorithm. We're simulating each point one at a time so we can account for the previously simulated grid cells and ensure that we have a continuous looking simulation. To quantify spatial relationships, we use the variogram, which characterizes the covariance or spatial variance between measurements as a function of their separation distance. So this curve is showing the increase in the variance between every pair of measurements as the distance between those data points increases. So data points that are close together have a low variance. Data points that are far apart, or 30 kilometers, have a very high variance because they're not strongly correlated. So we we use this metric to quantify this degradation and correlation between measurements that are far apart from each other. And we can, and then the sequential Gaussian simulation is designed to reproduce those spatial characteristics in the simulation. We've also created a function that allows us to cluster a region into different subregions, and we can characterize or define a separate variogram for each of those clusters and produce a simulation that that has different variograms throughout it. So this is useful for when we have an area where the spatial statistics might change, where the roughness is different throughout the region. And so we can do this pretty seamlessly. The main bottleneck in this algorithm is the nearest neighbor octant search. And this is a step where if you want to simulate a grid cell, you have to figure out what all of your nearest neighbor data points are so that you can condition that simulation to the nearby data. And it's an octant search because we want to search for data in every direction. Sometimes you might have a nearby flight line with a lot of measurements on only one side, but you want to make sure that you're looking in all directions to make sure that this simulation is not too heavily weighted to one side. So we need a more balanced, or we look in all directions so that our simulation is more balanced. And here is a profile of the simulation code using some NVIDIA tools. And this represents the time to simulate one grid cell. And each of these purple blocks is part of the octant search. So the search within each octant is one of these. So you can see that the majority of the computational time is dedicated to just searching for nearest neighbor points. And if we wanted to simulate something the size of Greenland, it would take about 5,000 hours to do one realization using this approach. And this is very problematic because then it would take years to produce large ensembles of realizations of or at ice sheet scales. So it's really important that we improve the speed of these algorithms. My lab participated in a hackathon hosted by the NVIDIA supercomputer company this spring, where we worked on adapting the sequential Gaussian simulation algorithm to run on a GPU, which is a very powerful type of computer. We were able to parallelize that octant search, so that cut our runtime by about 8. And through our GPU parallelization, we were able to come up with a projected 30 times increase in simulation speed. Our ongoing work is focused on parallelizing the sequential Gaussian simulation. So I mentioned earlier that this algorithm simulates one grid cell at a time, which is very inefficient for large areas like Greenland. And it also does not make this algorithm well suited to GPU computing because GPUs are designed to do large jobs in parallel. So with some tricks, we're actually able to almost entirely parallelize this sequential Gaussian simulation. And we can do that by say we have some simulation grid with these blue dots that represent data points. We can come up with a random simulation order. So these numbers represent the order that the grid cells are going to be simulated in. And then we can go to each grid cell at the same time and calculate all of the nearest neighbor distances to each of the data points and the previously simulated grid cells or grid cells with smaller numbers, and do all of those nearest neighbor calculations at the same time for each grid cell. And there are a lot of large matrix inversions involved in the simulation that we can also do in parallel using this approach. So that would give us an expected 1,000 times speed improvement for simulating large areas like Greenland. So at this moment, we're able to run this parallelized version on a CPU and are currently adapting this algorithm for GPU performance. So our hope is that in the coming months, we'll have highly efficient, very flexible open source algorithms to be used by the glaciology community. And with that, I'll take any questions. Thank you.
Thank you, Emma, for your talk, and the floor is open for questions. I don't see any raised hand, but I have a quick question, Emma. How do you cross-validate the results for the kriging or the other interpolation techniques or the algorithms you are practicing? I mean, are you interpolating the whole data, and or you interpolate only 60 to 70% of data and use the 30% for the validation?
Yeah, so because simulation has the opposite objective of kriging. We're not trying to get an accurate bed elevation value. We're trying to get realistic topography. And actually, the kriging algorithm is used to do simulation. We're just doing random sampling rather than looking at the mean. So we don't do any cross-validation with kriging just because they use the same mathematical base, but with opposite objectives.
Okay. Peter has
But
raised
it will
his hand.
exactly match existing values, so it's conditioned to known measurements.
Yeah.
Mickey, nice talk. Thank you very much. Quite interesting. Very interesting. Quick question: the amount of roughness that you're adding to the bed is probably proportional to the rock type. So if it's a harder rock type, it'll be rougher than a softer rock type. Is there any way you can weight it using any of the geophysical magnetics or gravitational information that you might have on the roughness that sort of can add some constraint to the roughness?
Yeah, that's a really interesting idea. Right now, we're just learning purely from the bed measurements, but we're setting this up so that we do this clustering analysis where we partition Greenland into different clusters and compute the variograms separately for each region, so that we can do simulations with regional variations in roughness that are learned from the data in those regions. But I think that, yeah, there are some very interesting directions where we can try and incorporate other geophysical data into this. But I also think there comes a point where it's like, where if you use too much information to constrain topography, it almost limits the scope of how you can use it. So we're still trying to figure out where that like happy optimal point is.
Thank you, Emma. And then it's time for the next presentation. Can you please stop sharing your screen?
Yes.
Christina Pedersen, who will speak on the Norwegian Infrastructure Initiative Troll Observing Network. Christina, please.
Thank you. Screen now, Shridhar?
Yeah, can you move it to the full screen mode? Yes.
Perfect. I'm Christina Pedersen from the Norwegian Polar Institute, and it's a pleasure for me to be able to introduce you to the new Norwegian Research Infrastructure Initiative, the Troll Observing Network. You all know that the Earth system is coupled, and Antarctica and the Southern Ocean are central drivers for both the Earth's ocean and the Earth system. And to be able to understand the entire Earth system, we need to have knowledge of the physical, biological, chemical, and geological processes taking place in the south. And in order to get this knowledge, we need to collect observational data. So to be able to understand the Earth system, we need observations. And despite all the research taking place in Antarctica, we lack long-term observations from several regions in Antarctica. So we saw that we could take a role here. So who are we? The Norwegian Polar Institute joined forces with several central research institutions from Norway and abroad, and developed a comprehensive research proposal to the Research Council of Norway on one of their largest call, namely the research infrastructure of national importance. We tried and developed a proposal in 2018. We got really good feedback, but no funding. But this positive feedback made us more eager, so we restructured the proposal and resubmitted in 2020. And just before Christmas last year, we received the best Christmas present ever, that our proposal was funded with almost 80% of what we asked for. Now we have revised the project and we have a 300 million Norwegian krone or 30 million euro project, where the Research Council of Norway financed more than half of that. So the Troll Observing Network, or TONE, or TONE in short, will collect data and generate knowledge from Dronning-Maudland, one of the most data-sparse regions in Antarctica. The network is centered around the Norwegian Troll Research Station, which is located on the slope between the coast and the inland plateau at around 1,300 meters above sea level. So through the TONE network, we will collect central observational data, make this data available for the Norwegian and the international research community, such that they can address basic questions about environmental and climate change and their impact on society. So the Troll Observing Network consists of 3 different parts. It's the 8 observatories ranging from the upper atmosphere through the solid earth and to the marine and biological environment. It contains of shared research infrastructure services, which is services that will be made available for researchers to use. And integrated in the infrastructure is a data management system, taking care of all the data that are collected and making it available for the researchers. I'll dig a bit more into the details of the observatories. First, the 4 atmosphere observatories, starting from the top with the ionospheric observatory, which is owned by the University of Oslo. It gives information about the complex coupling between the space and the Earth system. The ionosphere is also the place where space weather appear, and that influence, for example, satellite communication. So we will further develop the instrumentation that the University of Oslo has at Troll, with and complemented with DigiSonde. We move down the atmosphere column to the atmosphere chemistry observatory. So we know global changes are first seen at the poles. So it's important for us to measure air quality in the atmosphere at the poles and also in the south. So the Atmosphere Chemistry Observatory is a further development of the Atmosphere Observatory at Troll, which is run by the Norwegian Institute of Air Research. It was developed some 10-15 years ago. Here we measure the composition of the atmosphere, the season and yearly variation, and transport of polluted air to the area. And now we will extend it with more instrumentations. So a brand new activity for us will be the integrated cloud observatory. It will collect parameters on cloud and aerosol properties. It will be one of the very few stations with such a year-round program. So the integrated cloud observatory consists of new, passive, and active remote sensing instruments to measure temperature and humidity profile and cloud and aerosol characteristics. It also includes instrumentation for in situ validation of the remote sensing instruments and a radio sound system for balloon launches once daily. It will be a similar setup as the ice caps super-site at Summit, Greenland. The infrasound array will give information about and measure sound waves for atmospheric dynamic and vertical coupling between the different layers in the atmosphere. This is an infrastructure that will be owned by the Seismological Research Institute NOSAR in Norway, and it will be co-located with the seismic array, which is a solid Earth observatory. So earthquakes and other sources generate various seismic waves, which propagate through the bedrock. And these waves can be measured and used to image sources and structures in the ground. So in addition, we can measure seismic activity in the ice when, for example, icebergs collide with the continent. So a simple seismic station at Troll has shown that the area is one of the most sensitive areas to measure seismic activities in Antarctica, since it's both far from the coast and on fast ground. So we will complement the simple seismic station with a seismic array that will provide 3D information about the seismic activity and give estimate of amplitude, frequency, speed, and direction of the seismic signal. Over to the 3 observatories in the marine environment. So Fimbulisen is the largest ice sheet in Dronning-Maudland. During the International Polar Year in 2009, the Polar Institute and partners drilled and established localities for measurement of ocean properties in and under the ice sheet. So the instruments were believed to measure in 5 to 10 years, but they are actually still alive. So with FEO, we will do the drilling again and replace the instruments, and it will provide us with knowledge about the melting of the ice sheet, the ocean impact of the ice sheet, and the ice sheet response. The physical ocean system is strongly linked to the carbon cycle and the marine ecosystem. And we will be making observations to understand the processes and systems better. So with a multidisciplinary ocean mood observatory, we will further develop the multidisciplinary ocean mooring over the continental shelf at 6 degrees east. We will include new instrumentation, including sound sources for autonomous glider navigation under ice, and set up a more redundant system. And this monitoring will be supplemented with annual cruises. Finally, the 2 largest seabird colonies in Dronning-Maudland is by Svarthammen and utilise, and potentially more than 50% of the population of Antarctic petrel nest in Dronning-Maudland. And the Antarctic petrel eats mainly krill from the Southern Ocean. And by monitoring these Antarctic petrel colonies, we can take the pulse on the marine system in the Southern Ocean. And the seabirds function as so-called bioindicators or sentinels. So we will establish automatic monitoring of the birds colony with various camera system and weather station to provide information about the population, distribution, breeding success, status, and trends. To give you a better idea of the spatial distribution of the observatories, we have the 4 atmospheric observatories located at Troll Research Station. The Fimbul drillings will be done at 2 locations at Fimbulisen, 6.1 and 6.2, and they will do a pre-survey at a location further inland at 6.3. We will have the ocean moorings out at the location at 7.1, 7.2, and 7.3. And the seabird monitoring will take place at 2 locations at Svarthammen, close to Thor Field Station, and at Troll. But to complement and strengthen the data collection from the observatories at this location, we will establish a remotely piloted aircraft system service or drone service that will be able to supplement these observatories and collect data both horizontally and vertically and cover a large part of Dronning Maud Land. This will contribute to smart, cost-efficient data collection with a minimal footprint. So we have set up a system with 2 large multi-rotor planes that have good payload capacity and will be equipped with different sensor packages to do measurements for the cryosphere, the atmosphere, mammals, biomass and primary production, and geology. So under TUNA, the system will be established, tested, and validated. And as part of TUNA, there will be a larger pilot campaign in 26-27 where data will be collected. So the third and last part of the observing network is the data management system. So I will not go in detail here, but we will set up a dedicated TUNA web portal that will be the common entrance point to information about metadata collected in the observing system. Data users will get access to a dedicated user interface with a good search function where they can browse and access metadata. And we will also make TUNA data visible to the Antarctic Master Directory. So the implementation consists of 3 phases before we are operational. We are now in the procurement and testing at home phase. And already next season, some of the observatories will start to deploy. After that, we will go through a detailed validation and verification period where data will be quality assured, and we got a possibility to adjust the setups before we will be fully operational from 2027. I think I'll skip this. So what's in it for me, you may ask? So there's several ways you can access the TUNA infrastructure. It's possible to access the data. It's the long time series from the observatory and also the campaign-based data from the infrastructure services. It's possible to use the drone service either with the existing payload or you can bring your own payload. This will be a user-financed service. It's also possible to have campaigns on the instruments on the observatories to increase, for example, the data sampling frequency. And fourth, there is a general access to the Troll Research Station where you can access the station and the Polar Institute logistical services. This is open for all Norwegian and international researchers. So we are very pleased by the international Antarctic research community that really supported and endorsed our project in the application phase. In total, we actually received 39 support letters to our project, which we included in the application. And we are in no doubt that this helped us to realize the project to the full. So thank you very much. And now we cannot wait to really get going. With that, I will end my presentation today, and we promise to be back in 2 years with the first results. So I include my contact information here in case you have questions for me, and I also take some now, of course. Thank you.
Thank you, Christina. Thank you for such an ambitious project, and it is good to see so much of infrastructure coming up in next few years. I have a quick question about the remotely piloted aircraft system. Will that be the similar that we have in Longyearbyen?
Some of the system is similar as the Dornier flight, as the system set up on the Dornier flight. That is true. But this is a new capacity that will build up. But the Norse, which is our partner here, of course, have the drone infrastructure in Svalbard also, and they will take advantage and see on synergy. And there will also be testing out of equipment done on Svalbard.
Yes. Yeah. Thank you. Peter, do you have any question?
Yes, thank you, Christina. Very nice talk. Very interesting and ambitious project. If someone had wanted to access the facilities or you get some of the data, who should they talk to first? Is it yourself, or do they need a partner in NPI, or who do we go to?
No, as I said, we will set up a dedicated TUNA web portal, which will be the main entry point to access of data. This has not been done yet because we just started the project. So you can be in contact with me if you want, and then I will announce more details on the web portal when that is getting going. Shridhar, you are muted if you talked.
Oh, sorry. Thank you very much, Christina, for your presentation. And let's move to the next presentation. Thomas Schmid, can you please share your screen?
Sure, yes, hello. Can you see it?
It's appearing still. Yes, can you go to the full screen mode, please?
Okay. Can you see it now?
Yes, but not in the full screen. Yes, yes, now I can see.
Okay, it's a bit slow.
Yeah.
Okay. Welcome to the presentation of application of remotely sensed data and techniques to monitor terrestrial biodiversity within the Northern Antarctic Peninsula region. My name is Thomas Schmid. I work in a research center in Spain, Madrid, and I would like to acknowledge all my co-authors, which come from different institutions, from Germany, from the States, and also from Spain. So I would like to introduce our work. We work in the South Shetland Islands within the Northern Antarctic Peninsula region, which is a cold maritime climate. We particularly work in the ice-free areas that represent less than 3% of the total land surface area in that region. There's a concentration of fauna and flora where mosses and lichens are the main vegetation cover, and bird and seal colonies have their breeding grounds. At present, this region is one of the most rapidly warming places in the world over the past 60 years. Seasonally exposed terrestrial area is expected to expand up to 3 times its current size by the end of the century. And retreat of permanent ice cover will provide new habitats for flora and fauna to colonize. This will form big extensions by coalescing some areas that are currently isolated due to glaciers and permanent snowfields. So our objectives are to compile a site-specific spectral library for representative terrestrial soil surface covers for the South Shetland Islands. We aim to determine indicators of specific surface cover properties that determine the different stages of development within the ice-free areas and form the basis for monitoring environmental changes. We use the spectral library to identify different biodiversity factors and to monitor their distribution using the remotely sensed data. So up till now, our work has been characterizing these areas through geomorphological maps, We've used radar data to carry out supervised classification and then an extrapolation to further areas. The idea of using radar data is because it's not affected by bad weather or cloud cover, which is very common in this area. But we've also used multispectral data, which is within the visible near-infrared range, which is more affected by the cloud cover. However, we have been able to obtain data, and as you can see, we have carried out some studies where we've been able to determine certain surface covers within different areas. Now, the study areas I present in this work is mainly in Livingston Island, where we have Bias Peninsula and Heard Peninsula, which are marked in red squares on the map, and also Fielders Peninsula, which is part of King George Island. These are areas we have easy access and we can carry out our work. So each time we go on a campaign, we've been on numerous field campaigns, we can carry out work, and over the years we add more and more points to our spectral library. Our methodology is that we have, on one hand, in the figure on the left-hand side, we have field test sites. These normally consist of surface covers where we carry out the study of abiotic and biotic parameters. One of the main aims, of course, is to obtain spectra of the different surface covers. However, on the one hand, we carried out in the field with a spectroradiometer. On the other hand, we also take lab samples of soil, sediment, and we treat them in the laboratory also to obtain reflectance spectroradiometry. This all goes into a spectral library, and in the end, we associate this with lab analysis, with field observations to obtain a georeference database. On the right-hand side, we have our satellite-borne data. This can be multispectral or hyperspectral. Now, the hyperspectral is also over the optical and near-infrared spectral range. However, it has much more, many more spectral bands. It's to say the spectral resolution is much greater than in the multispectral data. So we have a much better definition of the different surface covers we want to register. Of course, we have to treat all this data, and our aim is to obtain reference spectra and to be able to identify them as end members, which then are used in supervised classifiers to obtain surface cover indicators. On the right-hand side of the slide, you can see the different field work we carry out. If we take for profiles, and we work with a spectroradiometer in the field under controlled conditions many times because of the bad weather, or also, if we're lucky, in natural conditions. We also use the spectroradiometer in the laboratory, and of course, this is with the aim of associating it, these spectra to satellite imagery. And the results of the Northern Antarctic Spectral Library, as we call it, the NAPSPEC, contains around 350 different spectra throughout the South Shetland Islands, and these are all in a georeference database. Here are some examples of lab spectra. So the soil samples were prepared to be able to take the spectra under control conditions. We have surface cover samples, which are just from the surface, or also soil profiles where we can actually look at the different horizons with the depth. And as you can see in the diagrams, we have the possibility to analyze these spectra and obtain different mineralogy, the organic matter, the different properties of the soils, and be able to assess them and then identify them. We can also, of course, the surface covers, if we're in the field, are not normally always bare soils, but covered with vegetation. So we also take these, and these are the actual indicators we're looking for, because if there's vegetation, we can also assume that there's a certain development of soils. With all these data, the spectra, and also the lab analysis of soil properties, we can carry out chemometrics. Now, with the chemometrics, it's very useful because the spectra actually obtains all the information of all the soil properties. However, if we can associate them with different types of analysis, this can be iron oxide, organic matter, the phosphorus content, nutrients, or the texture, then we can create models, regression models, and these models can be afterwards used to be able to actually determine the spectra of where the analysis are not, where the analysis have not been carried out. And this of course has a huge advantage because it's a much quicker method to be able to obtain an approximation of the different soil properties. So here's some examples where we've been able to apply this model and then obtain unknown spectra, soil properties of these spectra. Like this, we can actually carry out many more approximations and determine many more soil properties over a wider region. Now, our reference spectra, which we collect under field conditions, we normally try to obtain a homogeneous region of at least 3 pixels by 3 pixels of the type of sensor we're looking at. That means if a sensor has a pixel resolution, spatial resolution of 10 meters, 3 pixels by 3 pixels will be 30 by 30 meters that we have to obtain that area. And within that resolution, we select different points with a central point and the direction to the north, southeast, southwest, where we can obtain representative measurements over an area. And like this, we can obtain the field spectra you can see in the diagram, also over the region of the visible infrared, near infrared. And although with the atmospheric, the atmosphere affects these spectra, so we have certain regions of the spectra where there's no data. However, we can take this information out and obtain the spectra we're looking for. We can then apply this as we know the locations of these spectra and obtain the spectra from the multispectral image, for example. And here we have an example of different surface covers. They can be pavement, bare soil, stone, beach, mosses, etc. Also patterned ground. And like this, we can actually compare this to our reference spectrum. As we're looking for specific bioindicators, for example, I show here penguin rookery, where we've obtained the spectra in the field of the guano, which is deposited on the soil surface. And here we can actually look at the fresh guano, which is more the reddish, or also the whiter deposits, well reflected in the spectra. The difference. So knowing this information, which is very detailed, we can then go and see if in our images we can obtain this information. Here's an example of monitoring the fauna and fauna using the multispectral data. I've taken different examples. Actually, they're normally in the vicinity of penguin rookery, or where other types of birds have their nest. But of course, the surface covers will be many times influenced also by as is the case in green curve. And you'll see here the difference between Landsat 8 image, which is taken in 2018, and the Sentinel-2, which is taken in 2022. So this is where we're actually trying to see what changes have occurred between one date and the other. And as you can see from the spectra here, we do obtain differences. And actually what we're observing is that there's an increase in the vegetation cover in between the two dates. It's also, we of course have to take into account that these are different sensors. So to be able to compare what we're seeing in one sensor and the other, we have to carry out certain corrections. What is also important to consider is that the actual sun angle, when we're taking the measurements, can influence the spectral reflectance. So in 2018 compared to 2022, there's a difference in the intensity of the reflectance. It can be due to this problem of the sun angle. So there we would have to consider maybe a correction to be able to compare these data. When we come to the high spectral resolution data, it's not so long ago that these sensors have been put up into orbit. The Prisma data has been now in orbit for a little bit over a year. And when we went on a campaign this year, we actually we were not so lucky to obtain much data. We just obtained one image of a very specific area, and this is Fielder's Peninsula. And even then, we could not get the whole area of interest we're studying. So we do have limitations, but once we do have this data, we can see here a simulated data resampling of different types of surface covers, which would give us much more detail. And we're hoping that in the future, we'll be able to carry out a fine distribution of surface covers. And this is ongoing work to monitor the changes. So in conclusion, at present, terrain stability and environmental conditions allow a moderate evolution of the surface covers with soils and vegetation. The site-specific information and compilation of spectral libraries such as NAPSpec is considered important when working with remotely sensed data in the visible near-infrared data range. We need this reference to be able to identify what the satellite-borne data can give us. With regression analysis, models can serve to predict soil properties of spectra obtained from laboratory measurements. And the satellite-borne data enables a continuous monitoring of ice-free areas. Now, using future hyperspectral data will be an important step to characterize ice-free areas throughout Antarctica, including areas where direct accessibility in the field. Here I come to the end of my talk. I would like to give my acknowledgements for the support of this work through national projects of the Spanish R&D national plan, and also the logistic from the Spanish personnel, and also provided by the different Antarctic programs of Argentina, Chile, Korea, Spain, and Uruguay to carry out our work. I thank you and open to any questions.
Thank you, Thomas, for your talk. And since we are behind the schedule, I would request audience to put up your question in the chat box or the question box. And Thomas is here to answer these questions through the chat box. But then we move to the Next speaker, Jack Pan, who would share the screen now. Thomas, can you unshare your screen,
Yes,
please?
sure.
Thank you.
Okay, thank you very much.
All right, great. Can you all hear me?
Yes.
And you can see my screen?
Yes.
Perfect. Okay. Thanks for having me here, and thanks to the session organizers. My name's Jack. I'm a postdoc fellow at NASA's Jet Propulsion Laboratory, and today my talk is on a new method for remote sensing detection of sea surface glacial meltwater in the coastal oceans of the Western Antarctic Peninsula. So the long-term impact of glacial meltwater is being extensively studied, especially the effect on sea level rise. But there's a more immediate impact of glacial meltwater on local ecosystems. So this impact is still an open question. For instance, Dariusz and I did some of this early work in the Western Antarctic Peninsula, and they found the glacial meltwater extended over 100 kilometers offshore over the continental shelf. And that they also found a correlation between these freshwater masses and the phytoplankton biomasses. And we have also found a very similar correlation in the glacial marine fjord in this region. And that this relationship between meltwater and phytoplankton can also be found in other polar regions. For example, in Greenland, Arrigo et al. Found meltwater arrival is positively correlated with phytoplankton bloom initiation. And additionally, our prior work also found that the presence of meltwater is more than just changes in salinity. And the meltwater is also an important mechanism for delivering nutrients to surface ocean in Edward Bay. And that the amount of meltwater present has an impact on not only phytoplankton abundance, but also their community composition. So given these very important ecological impacts, there's a need to develop additional methods to monitor glacial meltwater and also to supplement existing field methods. So the potential for remote detection of meltwater comes from the optical signal. And we have done prior work in Edward Bay, which is a glacial marine fjord in the Western Antarctic Peninsula. And the four colored panels represent the cross section of the upper 200 meters of the fjord, and the head of the fjord and the glaciers are on the right side of each panel, and we're moving towards the Gerlache Strait, going towards the left side of each panel. So here we can see during both December and April, there's a distinct optical feature near the glaciers, and this is expressed in both particulate backscattering coefficient at 442 nanometers and beam attenuation coefficient at 660. And these optical features are not just some form of density artifact. Studies from the 90s also found the same optical features at this very location. So this is because of the entrained glacial nanoparticles present in the glacial meltwater. And these nanoparticles have been found to be ubiquitous in meltwater from all polar regions. So these findings offer a potential for remote detection of glacial meltwater from ocean color data. So in this study, our goal is to present the initial development of a model to map glacial meltwater at the sea surface. And here we will describe a machine learning approach using Modus Aqua data. The model results are confirmed with an extensive in situ data set compiled from the Western Antarctic Peninsula, and the data has also been applied to ocean color data to visualize surface glacial meltwater in the broader WAP region. The ground truth data in this study are discrete stable oxygen isotope data, or O18. It's one of the most cost-effective field methods for measuring glacial meltwater. And this data set was compiled from the Palmer LTER grid, the Palmer Station sampling sites, Potter Cove, and Grathra, and it represents one of the most comprehensive O18 data set from the WAP region. And the meteoric water fractions derived using the accepted method following these prior studies listed on the slide and through the set of mass balance equations. So to train the model, we need to first select an algorithm, and the selection process. For the selection process, we iterated through 36 different regression algorithms, including adaptive boosting, support vector machines, k nearest neighbors, gradient boosting, and so on. And the selected algorithm at the end is a random forest because of its performance and also because it's reasonably interpretable. So we also went through a hyperparameter search process, and we focused on the key hyperparameters, n estimator, which is the number of decision trees in a random forest, minimum sample leaf, which is the minimum number of samples that should be present in the leaf node after splitting the node, and the minimum sample split, which is the minimum number of data points in any given node in order to split it. And we also separated the entire data set into 80% to 10% to 10% as training validation and test subsets. So this way, the hyperparameter search will only be tested against the validation data set. So we can prevent the search algorithm to indirectly train the model to overfit to the validation data. And the correlation coefficients for the validation and the test subsets are very similar. So this means we did not overfit our model. And once when we determined the hyperparameters, we used all the data to train the final model, which resulted in an R value of 0.82 when we look at a one-to-one validation. So this is that row 1, column 1 of this validation matrix on the right. And we also compared each in situ data point with a spatially and temporally averaged data points. And this is by averaging more and more areas around the matching modus pixel, and also by averaging in more and more days around the sampling data depicted in this matrix. So initially, we really wanted to do this because the polar regions are cloudy and matchup data points are very scarce, as the other presenters pointed out. So we wanted to see how discrete in situ data points would compare with multi-day composites. And we got some very interesting results, as you can see here, as we averaging in more and more modus data in space, and over time, you start to get this threshold to form. And this means two things. One is that this provides some insights on the potential residence time and the spatial scale of glacial meltwater, which is about 3 days and 5 kilometers. And so this provides some information on what spatial and temporal resolutions are needed for future field campaigns and remote sensing missions to resolve glacial meltwater. And the second thing is, this means this meltwater product, when this meltwater product is integrated with other data sets, we would caution to keep the time and space scales consistent. And of course, here are some images when we apply this model to modus data for the Antarctic Peninsula summer month. And the panel A, D, and G on the left are surface glacial meltwater. Middle panels are chlorophyll. Right panels are SST. And you can see the meltwater would accumulate southward, and this is consistent with the flow of the Antarctic Peninsula coastal current, which hugs the coast. And in addition, there's also a glacial drainage north of Alexander Island into Margaret Bay, and our prior work in the surface of a fjord in Amber Bay have found meltwater can indeed accumulate in this way. And we found that there was generally more meltwater later on in the year than the growth season. And while this is not a focus of our study, I also want to point out the high meltwater content near Larsen A and B on the eastern side. And the high meltwater content also coincides with high chlorophyll A concentrations, and this is also consistent with prior studies. And we also want to note that while they're spatially similar, they're not the same at all. So this means our model is not just picking up chlorophyll signals as meltwater. And high meltwater content near shore also coincides with low SST. So this is consistent with prior studies, which found cold, fresh water masses near the coast. And we also applied this model to other platforms. So here's the model being applied to airborne hyperspectral data collected during the NASA Orcus mission using a PRISM instrument. And this particular image is from January 2016. Panel A is the derived meltwater contents from the airborne sensor overlay modus. And you can see there's a distinct front in both data sets immediately south of the 64 degrees latitude. And what's really interesting is we found an iceberg in the middle of this image. And you can see here in panel B is an enhanced RGB image. And the iceberg also has a trail of bricky bits. And panel C shows meltwater content around the iceberg. And this entire image depicted in panel D has an average of 3.9% meltwater, but the areas immediately around the iceberg has an average of 6.5%. So these results indicate this model is applicable across different ocean color platforms, and it shows the benefit of supplementing existing data sets with airborne remote sensing, which has much finer spatial resolutions. So in conclusion, we developed a new method for quantifying surface glacial meltwater in the Western Antarctic Peninsula. And we want to stress that this model is not intended to be a definitive method for quantifying glacial meltwater, but rather as an evolving model that will be frequently updated as more in situ data becomes available. And this method has been validated by one of the most comprehensive awaiting data set from this region. And we have demonstrated that it can be applied to multiple remote sensing platforms. And we hope this new tool can help achieve a better understanding of the broader polar region's ecosystem dynamics and the biogeochemistry. Thanks so much for your time.
Thank you, Jack, for your presentation. It was really interesting study. And with the more of Prisma data, I think you will get more results that can be compared with the MODIS data, I guess. But yeah, there is a quick question from Peter. Peter, can you unmute yourself?
Hi, Jack. I know we spoke about this in the past. I'm really
Yes, sir. Hi, Peter.
What's your next step? What were you going to do next? I'd be really interested to see. What you're going to expand out, try other data sets or different regions?
Yeah, Peter, I think there are a lot of different ways to go forward, and I think there are a lot of opportunities for further collaboration. So like you just mentioned, yes, we should definitely try to adapt this model to other polar regions. We have tried it with, the Arctic and other places in Antarctica, and the results seem to be very promising, but again, there's no validation. Another way to look at it is to do more laboratory-based experiments and measurements, because there are still a lot of intricacies behind why this algorithm will work, and that would require detailed field measurements and laboratory measurements. Yeah, I think those are the two approaches sort of to go forward.
You should keep in touch.
For sure.
Thank you, Jack. And then we move to the last presentation of today's session. Sagar, can you share your screen?
Yes.
Yes, can you go to the full screen mode?
Yes, is the full screen mode visible?
Yes.
Okay. Good evening, everyone. My name is Sagar Wankede, and I'm going to present my work on potential application of deep learning using multispectral satellite data for characterizing glacier surface facies in Antarctica. These are the basic contents. So glacier facies are essentially glaciological facies, and when identified on site, let me just highlight the. Okay, when highlighted on site, glaciological facies reveal these kind of surface classes. Now, when observed via satellite remote sensing based sensors, either using radar or multispectral optical data, we find variations in the kinds of surface facies characterizable. For example, within optical data, the dry snow region identified would generally encompass both the dry snow and frozen percolation zone mapped using radar data. In addition to the variations in identifiable facies, there are also inherent complexities when trying to apply multispectral optical data for mapping surface characteristics of glaciers. Some of these complexities involve around the two basic processes of image processing and information extraction. The primary objective or the presumption going with image processing is that the selection of one method is going to prepare the image in the best possible way to derive the most reliable or realistic spectral signature and the most easily discernible visual characteristics for the analyst or the algorithm to correctly classify the target features. And while we have a host of different information extraction algorithms present between pixel-based, object-based, and deep learning, a robust analysis of what kind of influences can be exerted by the image processing routines themselves on the resultant thematic maps is not robustly tested for glacier facies. Even so, resolution enhancement by pan sharpening or and what influences might that give, what and across different algorithms, what may be the effect for mapping glacier facies is not robustly tested. And all of this also boils down to the one major issue is if the method delivers the most accurate map, is that method really consistent across different glaciarized regions? Is the other methods transferable to different areas, or maybe even within the same sensor and across different glaciers? So these are some things that generally need to be taken into consideration when trying to map target features using optical data. And before applying the multispectral data for characterizing facies in Antarctica, we need to investigate what kind of exertions would these derive on mountain glaciers, because mountain glaciers generally try to show more facies at the end of summer. So we could try to see the variations in that and gain knowledge and then apply it in Antarctica. So in order to do this, we designed an experiment to study and characterize the glacier surface facies in selected glaciers in New Alisand, Svalbard, and in the Chandrabhaga Basin in the Himalayas. The design of the experiment is pretty straightforward. We have taken very high resolution worldview 2 satellite data. We used 3 different atmospheric corrections, the DOS, flash, and quack, and 2 pen sharpening methods, the GS and HCS. As a result of implementing these 5 methods, we have 9 different processing schemes when distributed across the 2 different study sites for 15 glaciers in total. Then all of these subsets are classified using 12 pixel-based classification algorithms, 5 conventional, consisting of from MHD, Marlow-Lopez distance to the winner-takes-all method, and 7 advanced classifiers, which start from the adaptive coherence estimator to the target constrained interference minimized filter. In total, we had about 1,620 classified subsets to assess and then validate. Now, these are pretty interesting results. The typical process would be we try to take an image of any feature, not just for a glacier, and try to identify how best we can visually identify or ascertain the feature that we want to map. Then possibly use an area of interest tool in any application to derive the spectral signature, and then compare it with the reference data or published literature, and then try to assign training samples accordingly. Here, the methods have given us a variety of variations in the resultant spectral signatures, and pan sharpening has resulted in a decrement of intensity in reflectance. And this is consistent across the board for all facies of and all across all glaciers. And this presents a kind of a problem, because now to analyze or to take signatures for input into the classification models, we need to ascertain what spectra can be used to reliably determine what facies is present here. upon checking literature, published literature, and hoods of data, we found that the reference spectral signature, the spectral signatures derived from the flash-corrected subsets, non-pan sharpened flash-corrected subsets, are more reliable and more realistic to what has already been proven for similar facies. Hence, we use that as to derive the training data and then apply the AOI based on that across all the different processing schemes into our classification models. These are some of the statistical results. We've just a brief, concise presentation of the results. For the atmospheric corrections using overall accuracy, while it is observable that the DOS correction has yielded the maximum accuracy compared to quack and flash method, it has also given the maximum variance across all the classifiers. So the DOS correction, while it may yield higher accuracy for maybe a single glacier, but in the same region or across different regions, it may not yield the same level of accuracy. However, the flash method seems to be pretty consistent for most, except for the MD and the SEM method. Across, except for these two, the flash has shown pretty consistent classification results. The quack is sort of a bargain between DOS and flash. DOS and quack are in-scene methods that don't utilize any kind of atmospheric model data or aerosol model data, whereas the flash utilizes a host of sensor elevation, sun angle, atmospheric and aerosol models to derive reflectors. Among the pan sharpening methods, clearly we see that used on error rates, all the pan sharpened classified subsets have really high error, and it's also due to the decrement in reflectance. Moreover, one interesting finding was that the MTTC-IMF classifier showed one improvement in classification after pan sharpening of the flash method. So the HCS pan sharpening for the MTTC-IMF for the flash corrected subsets showed an improvement in performance within the MTTC-IMF classifier. However, this was not enough to get to even overcome the DOS or quack classification results, the overall accuracy. So the pan sharpening really doesn't improve classification of glacier facies. But between HCS and GS, the HCS has delivered slightly better results in comparison to the Gram-Schmidt method. The most consistent classification algorithm that has given consistent results and better superior results across all processing schemes is the MXL classifier. These are some of the thematic maps from the classification carried out on Mithre Lowenbreen Glacier in New Ellis and Svalbard and the Samudra Tapu Glacier in Chandra Basin, Himalaya. Now, gaining the knowledge that we did from the experiment in those regions, the challenge is how do we apply everything that we've learned into trying to identify or characterize glacier zones in Antarctica. Most of the research centers around utilizing radar data, and that also means that we do not have that much satellite spectral libraries for which to refer from when trying to identify different glacier facies using optical data. So we thought of utilizing what we know. We use the flash correction and tried to map facies, what visible facies we could find for the polar record glacier. As these are just preliminary test results, as the experiment is still ongoing, and these are the first set of results. We tested two deep learning methods, a neural net classifier and support vector machine, and compared that to the conventional pixel-based classifier, that was SAM. So qualitatively, the neural net classifier does show some visually appealing results. We still need to quantitatively assess them, and that would be the next step. And from what we can identify, meltwater lakes, meltwater on snow, wet snow, and bare ice. Meltwater lakes are well categorized by both RNC and SVM and may hold some potential application for future. SAM has not delivered that good of differentiation. That was even seen in the other method applied in Svalbard and Himalaya. The SAM did not deliver that good classification results. So what are the future prospects and what is the conclusion? We know that now the flash atmosphere for the mapping of glacier facies, the flash atmospheric correction would generally give the more reliable reflectance signature. Then in combination with the MXL classifier, it may be employed to derive more consistent thematic maps across different glaciers for mapping glacier facies. A standalone high accuracy method may be the DOS, but it just needs to be tested on a few glaciers aside to try and see if it is consistent. Pan sharpening does not improve results. It only causes a decrease in performance. And the computational demand for carrying out this analysis is actually quite high because advanced classification algorithms and very high resolution satellite images, they end up taking a lot of space on the hard disk. When we assessed how much time and how much space was needed, it took around 14 months to generate all the data for 2 glaciers. And then for around 15 glaciers, it took, you can imagine the amount of time needed. So, and the total space storage, again, we had about 5 TB of storage space dedicated just for 2 glaciers. And then accordingly, the data storage also needs to be adjusted. So there is a computational limitation on carrying this out, but the results are promising. Optical methods for mapping facies need to be tested more robustly in Antarctica. Moreover, this has to be supplemented with spectral signatures. So hopefully, we should get to visit the field and collect signatures and then try and see how we can best map them using multispectral sensors and try to generate a spectral library. Deep learning does have a potential for generating some really nice and accurate pixel-based maps. However, one issue is if we try to scale it across different large number of glaciers, sometimes the reliance on training data can be an issue, as the role of the analyst is quite important in assigning training data in these algorithms. So in future, our goal would be to try and ascertain what method, what kind of atmospheric correction, what kind of pan sharpening method would best deliver good results for mapping facies in Antarctica. And we would also try to expand upon our work in the Himalayas and in Svalbard and try to cover different satellite data archives for more regions and create an inventory for glacier facies and present the results to the scientific community very soon. These are some of the references. And thank you for listening.
Thank you, Sagar, for the presentation. And I think we are well on time. Any questions from the audience? I understand it's too late and it's a 4-hour long session. If not, then we can move to the poster presenters if they would like to present their posters for a brief presentation, like 2 to 3 minutes. So anyone from the audience attendees who are the presenting authors of the posters, can you raise your hand or put up your, yes. Okay, Robert would like to present. So I would move him to the panelist. Yes, now Robert can share the screen if you would like to. Yes. Robert, can you share your screen so that you can present your poster? Yes.
So have you seen my poster?
Yes.
Okay, hi, I'm Robert Galik from the Institute of Biochemistry and Biophysics, Polish Academy of Sciences. And I would like to encourage you to take a look at our poster on which we present the results of sediment plumes observations that have been collected in Admiralty Bay on King George Island. We collect multispectral images with use of commercial RPAS with simultaneous observation of physicochemical parameters of seawater with use of CTD probe. If you have any questions, please contact me or my PhD student, Cornelia. And thank you for your attention and for all of today's presentation, which were very inspiring for me. Thank you.
Thank you. And I also request all the audience, all the participants and audience to go through the poster session, which is also available on the virtual platform. So I don't see any other poster presenter in attendees. So this means that we conclude our today's session. Peter, would you like to say something at the end, or we close the session? Before we close the session, you are muted, Peter.
Just like to say thank you again to everybody. Some really good talks there, a really good selection of different methods and new methods and remote sensing methods. I'm going to go and look at some posters. I think there's a few I haven't seen yet. Thank you, Shridhar, and thank you, Shridhar, as well, for organising and doing the bulk of the work in the convening of the session.
Thank you so much, everyone, and good night from at least from Svalbard, and see you after 2 years in the SCAR Open Science Conference. Thank you, and I will close the session.